Hey my friend, if your mind feels full tonight, you're in the right place. In this video, we'll drift through the most fascinating theories about how the universe began, ideas that blend real science with quiet wonder. Let the day fade. Get comfortable. And if you fall asleep while listening, well, that's exactly what this video is here for. Chapter 1. Why the Big Bang isn't the whole story. When people hear the phrase Big Bang, it often sounds like a complete story. The universe began from an unimaginably hot, dense state, expanded, cooled, and over billions of years formed stars, galaxies, planets, and finally beings like us who can look back and reconstruct that history. In modern cosmology, the Big Bang framework is not just a poetic image. It is a quantitative model that has passed demanding observational tests. Yet, as precise as it is, the Big Bang picture is not the final word on the origin of the universe. It describes how the universe has evolved from a very early state, but it leaves deep questions open about where that state came from, why it had the properties it did, and whether the story continues beyond what we currently call the beginning. In its modern form, often called the hot Big Bang model, this picture does not literally describe an explosion of matter into empty pre-existing space. Instead, it describes a state in which space itself was once much hotter, denser, and more uniform than it is today, and has been expanding and cooling ever since according to the equations of general relativity. Several strands of evidence support this view. Distant galaxies show a systematic redshift in their light, indicating that, on average, space between galaxies is stretching with time. The cosmic microwave background, a faint bath of microwave radiation that fills the sky almost uniformly, is consistent with being the cooled remnant of a once glowing plasma that filled the entire universe. Precise observations from satellites, such as the Planck mission, have mapped tiny variations in this background that match the predictions of a universe that was hot, dense, and nearly uniform early in its history. The Big Bang model also successfully explains the relative abundances of the lightest elements. When the universe was only a few minutes old, conditions were just right for nuclear reactions that fused protons and neutrons into hydrogen, helium, and small amounts of lithium. The observed ratios of these elements align closely with the calculations from Big Bang nucleosynthesis, reinforcing the picture that the universe did indeed pass through such a hot, dense phase. Taken together, the expansion of space, the cosmic microwave background, and the primordial element abundances form a coherent story. The universe has a history, and it was once very different from what we see around us now. Even so, observations that strengthen the Big Bang framework also highlight its limitations. When cosmologists evolve the equations of general relativity backward in time using the observed large-scale properties of the universe, they find that the density of matter and energy and the curvature of space-time grow without bound as one approaches an initial moment. In the mathematics, this point is called a singularity, a place where the theory itself breaks down and no longer gives meaningful answers. The Big Bang model, by construction, begins after this singularity, when the universe is already expanding and already filled with radiation and matter. It does not explain what the singularity really is, what happened before it, or even whether the notion of before makes sense in a physical way. There are also questions about the initial conditions that the hot Big Bang seems to require. The universe we observe on the largest scales is remarkably uniform in temperature and density. The cosmic microwave background has nearly the same temperature in all directions, with fluctuations of only a very small fraction of a percent. In a simple Big Bang model without additional ingredients, widely separated regions of the sky would never have had time to come into causal contact, meaning there would have been no opportunity for them to exchange radiation and come to the same temperature. This puzzle is known as the horizon problem, and it suggests that the starting conditions assumed in the basic Big Bang picture are finely tuned in a way that calls for a deeper explanation. A closely related issue is called the flatness problem. Observations show that on large scales, the geometry of space is extremely close to what cosmologists call flat, meaning that parallel lines remain parallel, and the angles of a large triangle add up to very nearly 180 degrees. In the equations of cosmology, this flatness corresponds to a delicate balance between the average density of energy in the universe and a critical value determined by the expansion rate. If the density at early times had been even slightly different from this critical value, the deviation would have grown over cosmic time, leading either to a universe that rapidly recollapsed or one that became extremely curved. The fact that we see a universe that is still very nearly flat today implies that in the early universe, the density must have been tuned extraordinarily close to the critical value. In the simplest Big Bang model, this is simply assumed as an initial condition. The model does not explain why the balance was so precise to begin with. The leading attempt to address several of these issues within the Big Bang framework is the idea of cosmic inflation. Inflation proposes that very early in the universe's history, there was a brief period during which space expanded at an accelerated, almost explosive rate, driven by a form of energy with negative pressure. In most models, this rapid expansion smooths out any initial irregularities, drives the geometry of space toward flatness, and stretches tiny quantum fluctuations into the seeds of the large-scale structure we see today. In this way, inflation is not an alternative to the Big Bang so much as a modification of its earliest moments, providing a possible mechanism for the initial conditions the hot Big Bang seems to require. Inflation itself, however, raises new questions. There are many different models of inflation involving different fields and potentials, and not all of them make the same predictions. While measurements of the cosmic microwave background are broadly consistent with the simplest inflationary scenarios, they have not yet singled out a unique model. Moreover, inflation as usually formulated still relies on an initial state that must be specified. It does not by itself eliminate the singularity or fully explain the ultimate origin of the inflating patch. Other open questions show that the Big Bang framework accommodates unknowns rather than resolving them. Most of the matter in the universe appears to be in some invisible form called dark matter, inferred from its gravitational effects on galaxies and clusters, but not yet directly detected in laboratories. An even larger share of the cosmic energy budget seems to be in a mysterious component called dark energy, responsible for the observed acceleration of cosmic expansion. The Big Bang model can incorporate dark matter and dark energy as additional terms in its equations, but it does not explain their fundamental nature. Similarly, the observed universe contains much more matter than antimatter, even though known particle physics tends to produce matter and antimatter in nearly equal amounts. Explaining this matter, Antimatter asymmetry requires processes in the early universe that go beyond the simplest assumptions of the model. At the deepest level, the Big Bang description rests on general relativity, a classical theory of gravity that treats space-time as a smooth continuum. Near the initial singularity, however, densities and curvatures become so extreme that quantum effects are expected to become important. A complete account of the universe's origin would require a theory that unifies quantum mechanics with gravity, something cosmologists and theoretical physicists have not yet fully achieved. Candidates such as loop quantum gravity and string theory suggest that the Big Bang singularity might be replaced by a bounce, a transition, or some other more benign structure. But these ideas are still under active development and have not yet been tested observationally. Until a consistent quantum theory of gravity is firmly established, any description of the ultimate beginning of the universe remains provisional. All of this means that, in modern cosmology, the phrase Big Bang is best understood not as the name of a complete theory of origins, but as the label for a successful, effective description of how the universe has evolved from an early hot, dense phase to the rich cosmic web of galaxies we see today. Within its domain of applicability, this description is extraordinarily successful and is supported by multiple independent lines of evidence. It gives us a narrative stretching from the first fractions of a second of known physics through the formation of atoms, stars, galaxies, and planets. At the same time, by confronting this model with ever more precise data, cosmologists are mapping its limits and identifying the places where it must be extended or replaced by a deeper framework. From a human perspective, there is something reassuring in this state of partial understanding. We know enough to trace the broad outlines of the universe's history and to see that we live in a cosmos governed by regular, discoverable laws. We also know that there are still genuine mysteries at the edges of our knowledge, from the true nature of the early universe to the origin of the laws themselves. Those mysteries need not be unsettling. They mean that the story continues, that there is more to learn, and that our present theories are stepping stones rather than final answers. As you listen to these ideas, you do not need to solve any of these puzzles yourself. The questions about singularities, dark energy, and the earliest moments of the cosmos will still be here tomorrow, patiently waiting for curious minds. For now, it is enough simply to know that the universe has a history, that you are part of that unfolding story, and that it is all right to set the questions down for a while. You can let your thoughts drift with the expanding universe, let the day's concerns recede like distant galaxies, and allow your mind to grow quieter as the cosmos around you keeps on evolving calmly in the dark. Chapter 2. The Steady-State Universe, a Cosmos with No Beginning. When the Big Bang model was still in its formative decades, there existed another contender for the story of cosmic origins, one so radically different in its philosophical implications that it still holds a certain poetic power today. This alternative was known as the Steady-State Universe, a vision of the cosmos that neither began nor will ever end, a universe that looks essentially the same at all places and at all times. It was proposed in the late 1940s by Fred Hoyle, Herman Bondi, and Thomas Gold, who were grappling with the same astronomical discoveries that would later secure the Big Bang as the dominant cosmological model. Yet they followed a different path. guided by a belief that the universe should not possess a preferred moment in time any more than it should possess a preferred location in space. Their proposal was bold, elegant in its internal logic, and for a period seriously considered by many astronomers. Even though modern observations have since ruled it out, the steady-state theory remains a crucial chapter in the history of cosmology. It helped shape the debates, sharpened the questions, and clarified what any successful theory of the universe must be able to explain. The steady-state model was founded on an extension of the cosmological principle, which states that on sufficiently large scales, the universe is homogeneous and isotropic. In simpler terms, the universe looks the same in every direction and from every vantage point if one averages over enough distance. Hoyle, Bondi, and Gold added another condition. The universe should also look the same at every moment in time, at least in its large-scale statistical features. They called this the perfect cosmological principle. If the universe is everlasting and unchanging in this very broad sense, then any observer living at any epoch would measure the same average distribution of galaxies, the same large-scale geometry, and the same overall cosmic conditions. According to this idea, the universe does not evolve on the largest scales. It simply persists. However, astronomical evidence had already shown that galaxies appear to be receding from us, with more distant galaxies moving away faster. This pattern, codified as Hubble's law, strongly suggests that the universe is expanding. In a universe that expands, the average density of matter should decrease over time unless something replenishes it. To maintain the perfect cosmological principle in an expanding universe, the steady-state model required the continuous creation of matter. Hoyle introduced this idea explicitly, proposing that new hydrogen atoms appear spontaneously in space at a rate just sufficient to keep the density of the universe constant as galaxies move apart. The required rate of creation is extremely small, only about 1 hydrogen atom per cubic meter over many billions of years. With such a minute rate, no known laboratory experiment of the time could possibly detect the process directly. In the steady-state model, this slow creation was not a dramatic explosion, but rather a gentle and persistent seeding of the cosmos with fresh matter. Once new matter appears, gravity can draw it into clouds that eventually form new stars and galaxies. In this picture, even though individual galaxies age and evolve, the overall population of galaxies across space and time remains statistically unchanged. New galaxies continually form from the newly created hydrogen, replacing older galaxies that might have collided or faded. The universe, then, is eternal and unchanging in its large-scale structure, even though smaller-scale objects experience birth, evolution, and death. At the time it was proposed, the steady-state model had appealing features. It avoided the need for a singular beginning, something many scientists found philosophically troubling. It treated all moments in time on equal footing, maintaining a kind of temporal symmetry that seemed natural to its proponents. And because the rate of matter creation was so small, Hoyle and his collaborators argued that it need not violate conservation laws if one viewed the universe as a whole. They suggested that conservation of energy might apply differently in general relativity, where the geometry of space-time itself can change over time. These arguments were debated, but they allowed the theory to be taken seriously. For a time, observational evidence did not decisively favor one model over the other. Early galaxy surveys were limited in scope, and measurements of cosmic distances were plagued by uncertainties. Some observations even seem to support the steady-state idea. For instance, radio astronomy in the mid-20th century uncovered many bright radio sources whose nature was initially unclear, and some early interpretations could be reconciled with steady-state expectations. Because the steady-state model predicted that the universe today should look much the same as it always has, it implied that the population of distant galaxies should not differ significantly from those nearby. That prediction could only be tested once telescopes became powerful enough to see very far into the universe. As the observational capabilities of astronomers improved, however, cracks began to appear in the steady-state framework. Deep galaxy surveys revealed that the universe does indeed evolve with time on large scales. Distant galaxies, seen as they were billions of years ago due to the finite speed of light, appear younger and more irregular than nearby galaxies. Star formation rates were higher in the past, and large-scale structures such as galaxy clusters show clear signs of evolution. These discoveries contradicted the steady-state prediction that the universe should look the same at all epochs. Another major challenge arose from the discovery of the cosmic microwave background. In the mid-1960s, Arno Penzias and Robert Wilson detected a faint, nearly uniform microwave signal coming from all directions. This discovery was precisely what the hot Big Bang model predicted: the cooled remnant of a once hot, dense plasma. The steady-state model, by contrast, had no natural mechanism to produce such radiation with its observed properties. Various attempts were made to reinterpret the microwave background within the steady-state framework, including proposals involving starlight scattered by intergalactic dust, but none could match the smoothness and spectrum of the observed radiation. The microwave background became the decisive evidence that the universe had indeed undergone a hot, dense phase in its early history, something incompatible with an eternal steady-state cosmos. Further evidence against the steady-state theory came from studies of quasars and radio galaxies. Quasars, among the most luminous objects in the universe, were found to be far more common at great distances than nearby, indicating that they were much more abundant in the early universe. This strong evolution with cosmic time was at odds with the predictions of a steady-state universe. By the late 1960s and early 1970s, the weight of observational evidence had shifted strongly in favor of the Big Bang model. Yet the steady-state theory left an enduring legacy. It forced cosmologists to think deeply about how observations test large-scale models. It highlighted the importance of understanding galaxy evolution and the significance of radio astronomy. And it inspired later theoretical work, including Hoyle's own contributions to astrophysics, notably in the field of nucleosynthesis. Even though the steady-state universe is no longer considered a viable cosmological model, it remains an instructive example of how science advances. The theory was mathematically coherent, physically motivated, and initially compatible with available data. Its eventual decline was not due to philosophical disagreement, but to the accumulation of precise measurements that it could not accommodate. This illustrates a central principle of scientific progress. Theories must ultimately confront the full range of empirical evidence, and it is the universe itself that delivers the verdict. Today, cosmologists understand that the universe does evolve significantly over cosmic time. The rate of star formation, the distribution of galaxies, the temperature of the cosmic background, the abundance of quasars, and the growth of large-scale structures all reflect a dynamic universe with a history. The notion of continuous matter creation has been replaced by ideas grounded in quantum field theory and general relativity, and the hot Big Bang remains the foundation for modern cosmology. Yet even within the Big Bang framework, new questions arise about what came before, whether time itself had a beginning, and whether the universe could undergo cycles. Some of these ideas echo the philosophical motivations that once drove the steady-state theory, showing that even a discarded model can influence how scientists think about the cosmos. There is also a deeper human resonance in the steady-state vision. The idea of an eternal universe, unbounded in time and continually renewing itself, speaks to a longing for stability in the face of change. It suggests a cosmos that simply is, without origin or end, indifferent to the passage of ages. Even though observations now tell us that the universe has evolved and that it once passed through a radically different phase, the steady-state model reminds us that scientific theories often begin as reflections of deeper intuitions about nature. Those intuitions may ultimately be overturned, but they play a role in guiding inquiry and framing the questions we ask. As you reflect on this early attempt to describe the cosmos, you may sense something calming in the sheer scale of these ideas. The universe, whether evolving or eternal, remains vast beyond comprehension. Its changes unfold over timescales that dwarf everything in human experience. Whether the cosmos has a beginning or stretches infinitely into the past, our daily concerns occupy only the smallest of moments in an immeasurable expanse. You can let that perspective soften the edges of the day. You are, after all, part of a universe that has persisted through epochs far longer than any single life. And in that knowledge there is a quiet sense of continuity, a space in which your thoughts can settle and your breath can slow as the night deepens around you. Chapter 3. Eternal Inflation. The universe as one bubble in an endless foam. In modern cosmology, inflation refers to a brief period of extraordinarily rapid expansion in the very early universe. This idea, first proposed in the early 1980s, was not originally meant to describe multiple universes or branching realities. Instead, it was introduced to explain specific features of the observable cosmos, such as its large-scale uniformity and near-flat geometry. Over time, however, inflation developed a deeper and far more surprising implication. Under certain conditions, it does not end everywhere at once. Instead, while inflation stops in some regions, allowing them to form ordinary universes like our own, it continues in others, creating a vast and potentially infinite multiverse. This expanded idea is called eternal inflation, a framework in which our universe is only one bubble among countless others forming within an ever-growing cosmic sea. Eternal inflation arises from the physics that govern the hypothetical field responsible for inflation, often called the inflaton. Although the precise nature of this field is not yet known, its behavior can be described in terms of quantum field theory and general relativity. In many inflationary models, the inflaton occupies a high-energy state that drives accelerated expansion. As it evolves, the field rolls toward a lower energy configuration, and when this transition completes, inflation ends locally. The energy stored in the inflaton converts into particles and radiation, initiating a hot, dense universe that then expands more slowly, following the familiar thermal history described by the Big Bang framework. This picture, however, becomes more complex when quantum effects are included. In quantum field theory, fields do not behave like smooth, continuous surfaces. They fluctuate. These fluctuations mean that the inflaton does not roll downward uniformly everywhere. In some regions, the field advances and inflation ends, but in others, the field fluctuates upward or remains in a high-energy state long enough to keep driving accelerated expansion. The expansion rate in those high-energy regions is so dramatic that they grow faster than the regions where inflation has ended. As a result, even though pockets of space transition out of inflation, the total volume undergoing inflation continues to increase. This is the key feature of eternal inflation. The inflating regions expand exponentially and dominate the total volume of the cosmos, even as isolated bubbles form, where inflation stops and ordinary cosmic evolution begins. Each of these bubbles is, in effect, a universe with its own initial conditions. What we call the universe is simply one such bubble. Our observable cosmos corresponds to a region inside that bubble, bounded by the cosmic horizon defined by the speed of light and the finite age of space as we can measure it. The implications of this model are astonishing. If inflation is eternal into the future, then bubble universes will continue to form endlessly, each disconnected from the others by rapidly expanding space. These bubbles can collide, though such collisions would leave distinctive patterns in their microwave backgrounds, and searches for these signatures are ongoing. If inflation is also eternal into the past, as some models propose, there may have been no beginning at all. The expanding inflationary background could itself have existed indefinitely, producing bubbles without requiring an initial singularity. Other analyses suggest that eternal inflation cannot be extended indefinitely backward in time, implying that even this multiverse would have some sort of beginning. The question remains under active research. Within individual bubbles, the end of inflation gives rise to a hot, dense state, resembling the early universe described by the Big Bang model. Yet because each bubble nucleates in a slightly different way, depending on the quantum state of the inflaton, the resulting universes may have different properties. The physical constants, particle masses, or types of fields present could vary from one bubble to another in certain versions of the theory. This leads to a picture known as the multiverse, a vast collection of isolated cosmic regions, each with its own physical laws. None of these universes can communicate with one another because the space between them expands faster than signals can travel. They form a cosmic archipelago, forever separated, each containing its own galaxies, stars, and histories. Supporters of eternal inflation point out that it naturally explains why our universe appears finely tuned for the formation of complex structures. If different bubble universes have different physical constants, then only some will have conditions suitable for long-lived stars, stable matter, and the intricate chemistry needed for life. We observe a universe compatible with these conditions because only in such a universe could observers arise in the first place. This reasoning is often called anthropic selection. It is not a conventional scientific explanation, since it lacks direct testability, but within the context of a multiverse, it provides a logical interpretation of otherwise puzzling coincidences in cosmology and particle physics. Although eternal inflation is a theoretical framework rather than a complete physical model, it finds support in the fact that many different inflationary potentials naturally produce self-perpetuating expansion. Eternal inflation is not a single theory, but a general class of scenarios. Different potentials describing the inflating field lead to different behaviors, but many share the same underlying feature. Quantum fluctuations occasionally keep inflation going in some regions even after it ends in others. This commonality makes eternal inflation a robust prediction of a large family of inflationary models. Observationally, eternal inflation is challenging to test directly because the bubble universes it predicts lie beyond our cosmic horizon. We cannot see into other bubbles, and the exponentially expanding space between them prevents any exchange of information. However, subtle clues might exist. Some models predict that bubble collisions could leave imprints in the cosmic microwave background, though no definitive evidence has been found. Other tests rely on studying the statistical distribution of fluctuations in our own universe to infer whether they could have arisen from conditions compatible with inflationary potentials that exhibit eternal behavior. These probes remain indirect, but as observational instruments improve, cosmologists continue searching for signatures that could favor or rule out eternal inflation. The idea of an inflationary multiverse intersects with deeper questions in theoretical physics, particularly in the context of quantum gravity and string theory. In string theory, the landscape of possible vacuum states is vast, potentially numbering an enormous array of configurations. Eternal inflation might populate these vacua, with each bubble universe settling into a different configuration. This provides a mechanism for exploring the full space of possible physical laws, though it also raises questions about predictability. If every possible set of physical laws occurs in some bubble, then explaining why our universe has any particular set becomes a matter of statistical reasoning rather than deriving them uniquely from theory. One conceptual challenge concerns probability. In a multiverse where the inflating regions grow without bound, defining probabilities becomes problematic. If there are infinitely many universes of all types, then comparing their relative frequencies becomes mathematically subtle. This issue, known as the measure problem, remains one of the most debated aspects of eternal inflation. Different proposals for regulating infinities yield different predictions, and there is no consensus about how to resolve this ambiguity. This difficulty does not invalidate the idea of eternal inflation, but it underscores that the concept requires careful mathematical interpretation. Eternal inflation remains one of the most compelling attempts to extend our understanding beyond the observable universe. It explains how regions like ours can emerge from a broader, high-energy background. It provides a framework for thinking about cosmic diversity, linking cosmology with questions about the origin of physical laws. It challenges assumptions about uniqueness and finality, suggesting that what we call the universe is merely a local phenomenon in a much grander structure. Even if eternal inflation is ultimately replaced by a more complete theory, its conceptual impact is profound. It reframes our sense of scale. The observable cosmos, with its hundreds of billions of galaxies, becomes a small and perhaps typical part of a far deeper and richer cosmic architecture. The idea that our universe might be one bubble among countless others stretches the imagination, but it arises naturally from applying well-established physical principles to the earliest moments of cosmic history. It shows how subtle quantum fluctuations, magnified by expansion, could give rise to a mosaic of universes, each with its own destiny. As you reflect on this vast and continually unfolding picture, you may feel both humbled and comforted. If the cosmos is an endless sea of expanding spaces, then our world is a delicate bubble floating in a boundless expanse, shaped by chance, yet governed by deep laws. Your life unfolds within one small corner of that bubble, brief compared to cosmic timescales, yet meaningful in its own frame. When you let your mind drift across the idea of infinite universes blossoming in silence, you might feel a gentle loosening of the day's concerns. In the quiet of this moment, you are part of a reality far larger than anything the eye can see, and there is a calm in knowing that the universe carries on, endlessly expanding, endlessly creating, far beyond the horizon of our little world. Chapter 4. The Multiverse from Inflation, Other Universes with Other Laws. Inflation as a theoretical framework began as a solution to specific puzzles in early universe cosmology. Yet when physicists explored inflation more deeply, they found that in many of its formulations, the process does not simply produce one universe. Instead, inflation naturally leads to a picture in which innumerable cosmic regions form, each effectively sealed off from the others, and each potentially endowed with its own physical constants and properties. This expanded view, often called the inflationary multiverse, has become one of the most discussed implications of modern cosmology. Although the concept reaches beyond what direct observation can confirm, it arises from well-studied mechanisms in quantum field theory and general relativity, and follows as a nearly unavoidable consequence of many inflationary models. The key idea behind the inflationary multiverse is straightforward in its broad outline. In the inflationary scenario, a field with high energy density drives a period of accelerated expansion. When the field eventually relaxes to a lower energy configuration, inflation ends locally, allowing the region to heat up and follow a conventional Big Bang-like evolution. What makes this process produce a multiverse is the fact that the transition does not occur everywhere at the same time. Quantum fluctuations alter the evolution of the field in different locations, causing inflation to end in a patchwork pattern. In some places, the field decays quickly, and those regions become bubble universes. In others, inflation continues for much longer, causing the surrounding space to expand so rapidly that the newly formed bubbles cannot catch up with one another. Each bubble contains an entire universe, complete with its own space-time, matter, and radiation. The region inside a bubble evolves much like a closed world, and observers within it perceive their own cosmic horizon beyond which they can never see. In this way, what we call the universe is really just one bubble in an immensely larger structure. Other bubbles remain forever inaccessible because the space between them expands faster than any signal can propagate. A central consequence of this picture is that different bubbles may not share the same physical laws. The idea that the constants of nature can vary is not arbitrary speculation. It arises from how high-energy physics describes the vacuum. In quantum field theory and in string-theoretic frameworks, the vacuum is not a simple, uniform emptiness. Instead, it is defined by the configuration of fields and energy states. And different vacuum states can lead to different effective physical constants. The strength of the electromagnetic interaction, the masses of fundamental particles, the ratios between forces, and even the number of dimensions that emerge in low-energy physics could differ from one vacuum state to another. When inflation produces bubbles that settle into different vacuum states, each bubble inherits a different set of physical parameters. One bubble may have a universe where the cosmological constant is extremely small, permitting galaxies, stars, and planets to form. Another bubble may have a much larger cosmological constant, causing space to expand so rapidly that matter never clumps together. A third bubble might contain physical constants that prevent stable atoms from existing at all. In this sense, the inflationary multiverse becomes a vast landscape of universes, each with its own internal rules, only some of which permit the emergence of complex structures like stars, chemistry, and life. The idea that many universes exist with different physical laws is not put forward to explain away difficulties, but rather emerges naturally from the mathematics of the underlying theories. In some models of high-energy physics, particularly those influenced by string theory, the number of possible vacuum states may be extraordinarily large. Inflation provides a mechanism for exploring this landscape. As it proceeds eternally, it continually generates new regions that fall into different vacua. Because the process does not end everywhere at once, there is always room for additional bubble universes to form. In this sense, the multiverse is not a hypothesis added for philosophical reasons. It is the natural result of a dynamical process. One of the most intriguing aspects of the inflationary multiverse is the way it reframes the question of fine-tuning. Many physical constants in our universe appear delicately balanced to allow the formation of complex structures. Slight deviations in some of these constants could render the universe sterile. The mysterious smallness of the cosmological constant, the relative strengths of the fundamental forces, and the mass ratios of elementary particles all play decisive roles in shaping cosmic evolution. In a single universe model, these coincidences can seem difficult to explain, but in a multiverse, they become less mysterious. Observers naturally find themselves in a universe whose constants allow observers to exist. Other universes with incompatible constants also exist but cannot host observers. This line of reasoning is often called the anthropic principle. It does not predict the constants of our universe from first principles. Instead, it argues that when the multiverse offers a large ensemble of possibilities, the existence of observers selects a narrow subset of universes compatible with observation. Although this reasoning remains controversial, it does provide a framework for interpreting certain otherwise puzzling features of the cosmos, including the small positive value of the cosmological constant. There are, however, significant scientific challenges associated with the multiverse concept. One of the deepest is the measure problem. If the multiverse contains infinitely many bubbles, and if new bubbles form eternally, then one must define probabilities over an infinite set of possibilities. Different ways of regulating or interpreting these infinities lead to different answers. This ambiguity complicates efforts to make predictions within the multiverse framework. Scientists continue to explore how quantum cosmology, decoherence, and various approaches to quantum gravity might offer clearer foundations. Observationally, the inflationary multiverse is difficult to test directly. The regions it predicts lie beyond the observable horizon, and no signal can cross the inflating boundaries that separate bubbles. However, indirect evidence may exist. For instance, If two bubble universes collided in the early stages of formation, such an event could leave an imprint on the cosmic microwave background. Researchers have searched for such signatures, specific circular patterns or discontinuities, though no conclusive evidence has been found. Other potential clues arise from studying the statistical properties of cosmic fluctuations. If the structure of inflationary potentials required for eternal inflation has distinct observable consequences, then precision measurements of the microwave background and large-scale structure could help differentiate between models. The inflationary multiverse also intersects with attempts to unify quantum mechanics and general relativity. In many quantum gravity models, space-time itself can take on different configurations or geometrical structures. The idea that inflation can populate this array of possibilities provides a bridge between high-energy physics and cosmology. Although the details remain speculative, the conceptual integration of cosmology with quantum foundations continues to be an active area of research. Despite these uncertainties, the multiverse remains a compelling possibility. It is widely discussed not because it is philosophically attractive, but because it emerges from well-motivated physics. If inflation occurred, and if the inflaton field obeyed the dynamics predicted by quantum field theory, then eternal inflation and the consequent multiverse are difficult to avoid. This does not mean the multiverse is proven. Theories must ultimately align with observational data, but the inflationary multiverse shows how much richer the cosmos could be than the part we can observe. It also reshapes our sense of what a fundamental explanation might look like. Instead of expecting one unique universe determined by one unique set of physical laws, the multiverse suggests that physical reality may contain a wide variety of possibilities. Our universe might simply be one example drawn from a much broader spectrum. This perspective aligns with the statistical nature of quantum mechanics and the probabilistic frameworks used in modern theoretical physics. It also encourages humility. The laws we observe may not be the only laws that nature permits. At the same time, the multiverse raises philosophical questions about meaning, identity, and the nature of existence. If countless universes exist, each with its own structures and histories, what does that imply about our place in reality? Does the existence of many universes diminish the significance of this one? Or does it enrich our understanding by showing how rare and remarkable the conditions for life may be? In one sense, knowing that many universes could exist does not change the fact that we live in this one, governed by the laws we have measured and shaped by an evolutionary history that has produced stars, planets, and conscious beings. As you contemplate the inflationary multiverse, you might notice a curious mixture of grandeur and intimacy in the concept. The scale is almost unimaginable. A cosmic expanse where entire universes appear like bubbles in a vast and ever-expanding sea. And yet, despite the enormity of that vision, your life remains grounded in a small, familiar world filled with experiences that matter to you. Perhaps there is something calming in recognizing that even if an infinite foam of universes surrounds us, we need only inhabit this one. You are part of a cosmos that may be far larger than anything you will ever see. And in that realization, there is a quiet sense of perspective, a reminder that while existence may be vast, your presence within it is singular and irreplaceable. Chapter 5. The Big Bounce. The universe with no beginning, only cycles of collapse and rebirth. In standard cosmology, the history of the universe begins with an initial state of extremely high density and temperature, followed by expansion and cooling. This framework has been remarkably successful at explaining observations such as the cosmic microwave background and the distribution of galaxies on large scales. Yet the Big Bang model, taken literally, leads to a singularity, a point at which densities and curvatures become infinite, and the known laws of physics lose their meaning. Most cosmologists regard this singularity not as a physical entity, but as an indication that the mathematical description being used has reached its limits. The Big Bounce idea emerges directly from this recognition. It proposes that instead of beginning in an unexplained singularity, the universe transitioned from a prior phase of contraction into the current phase of expansion. Rather than representing the absolute beginning of existence, the Big Bang becomes a moment of transformation, a bounce within a much longer cosmic cycle. The Big Bounce is not a single theory, but a broad family of cosmological models. These models share the prediction that when space-time reaches extremely high densities, quantum gravitational effects become dominant. Under such conditions, gravity may become repulsive rather than attractive, preventing matter and energy from collapsing into a point. Instead of forming a singularity, the universe undergoes a rebound. After contracting for an immense duration, the universe reaches a minimum size and then begins expanding again. In this view, the history of the cosmos may consist of repeated cycles, each containing phases of expansion, evolution, collapse, and bounce. One of the most influential frameworks for exploring the Big Bounce is loop quantum cosmology, an offshoot of loop quantum gravity. In loop quantum gravity, space-time is not treated as a smooth continuum, but as a network of discrete structures at the smallest scales. This discreteness leads to new gravitational behavior when densities approach the Planck regime. Instead of diverging toward infinite curvature, the gravitational field saturates and a repulsive contribution appears. Studies within this framework suggest that a contracting universe will reach a finite maximum density and then undergo a quantum bounce, emerging into a new expanding phase. These calculations show that the Big Bounce is not simply a speculative idea, but a mathematically grounded consequence of certain approaches to quantum gravity. Another path to bounce cosmology arises in modifications of general relativity. Some proposed extensions to Einstein's equations introduce additional terms that can dominate at high curvature, altering the behavior of space-time at extreme densities. Such models can produce non-singular transitions from contraction to expansion. In some scenarios, these modifications are temporary. At ordinary energies, the laws of gravity behave identically to general relativity, preserving the well-tested predictions of the theory. Only near the would-be singularity do the corrections become significant enough to prevent collapse. This allows bounce models to be compatible with both the successes of general relativity and the need for a new description of the earliest moments of the universe. A third approach to bounce cosmology emerges from high-energy physics and string theory. In certain string-inspired models, the geometry of extra dimensions or the behavior of scalar fields can produce contracting phases that rebound into expansion. These scenarios often involve exotic forms of energy or interactions that violate classical assumptions about how matter behaves under gravitational collapse. In some cases, brain-world cosmologies propose that collisions between higher dimensional surfaces can mimic the effect of a bounce, creating a new expanding universe from the debris of a previous collapse. Although mathematically intricate, these models highlight the wide range of mechanisms through which a bounce might occur. From an observational standpoint, bounce cosmologies must reproduce the successes of the hot Big Bang model while also providing distinctive signatures. One of the key questions concerns the origin of the nearly scale-invariant fluctuations observed in the cosmic microwave background. These fluctuations serve as the seeds for the formation of galaxies and clusters. Inflationary models explain them through quantum fluctuations stretched to cosmic scales. Bounce models, however, offer an alternative. In some scenarios, fluctuations in the contracting phase can pass through the bounce and become the seeds of structure in the expanding phase. The precise details depend on the mathematics of the bounce, but certain models predict characteristic patterns that might eventually be distinguishable from inflationary predictions. Another challenge involves entropy. In a cyclic universe where expansions and contractions repeat indefinitely, entropy would accumulate from cycle to cycle. This accumulation could make each successive cycle longer and larger than the previous one. While this does not rule out cyclic models, it complicates the idea of an eternally repeating cosmos with identical cycles. Some bounce scenarios circumvent this issue by positing that information is diluted in the contracting phase, or that entropy is reset during the bounce through mechanisms not yet fully understood. The resolution of this challenge remains an active area of research, tying together thermodynamics, quantum information, and cosmology. Despite these difficulties, the Big Bounce remains appealing because it addresses the most uncomfortable feature of the standard Big Bang model: the existence of a singularity. Singularities signal a breakdown of physical laws rather than a well-defined beginning. A bounce replaces this breakdown with a transition that is more consistent with the expectation that fundamental physics should remain meaningful even at the highest densities. It also provides a conceptual framework in which the universe need not have emerged from nothing. Instead, it becomes a participant in an ongoing cosmic rhythm, with each cycle connected to the next by deep physical principles. The implications for cosmology and philosophy are significant. If the universe undergoes cycles, then the observable cosmos represents only one chapter in an unimaginably long story. Each collapse would erase much of the previous structure while preserving certain features that shape the next expansion. The universe we inhabit could be influenced by conditions that existed long before the current expansion began. This raises intriguing possibilities. Perhaps certain large-scale features of the cosmos reflect patterns inherited from earlier cycles. Or perhaps the constants of nature are shaped by dynamics that unfold across multiple bounces. For some models, the bounce is asymmetric, with the contraction phase differing from the expansion phase. In these cases, the cosmic arrow of time may emerge from the dynamics of the bounce itself. Time might not extend infinitely into the past in the way we commonly imagine. Instead, the physical meaning of time could shift during the bounce. This challenges intuitive notions of before and after, emphasizing that our everyday experience of time is only one aspect of a much deeper and more complex reality. Not all versions of bounce cosmology are cyclic. Some propose a single bounce. The universe contracted from an earlier phase, reached a minimum, and then expanded into the cosmos we observe. Others entertain the idea of multiple bounces, but not necessarily infinite repetition. In all cases, the central message remains the same. What we call the beginning may not be the absolute beginning. Instead of a creation event, the Big Bang becomes a transition, a boundary between two epochs governed by quantum gravitational effects. Because bounce models arise from different branches of theoretical physics, they continue to evolve as researchers refine the underlying mathematics. Loop quantum cosmology has produced some of the most detailed bounce predictions, suggesting that the scale factor of the universe never reaches zero, and that a well-defined evolution can be traced across the bounce. High-energy models and string-inspired scenarios contribute additional possibilities. Although no observational test has yet singled out a unique bounce model, the growing precision of cosmological measurements continues to narrow the parameter space in which these models operate. Ultimately, the Big Bounce invites us to rethink the nature of cosmic origins. Instead of a universe bursting forth from a singular, uncaused moment, we encounter a cosmos shaped by deep physical processes that operate across cycles or transitions. The universe becomes not an abrupt emergence, but an ongoing evolution. In this view, existence does not spring from a single moment of creation, but flows through a larger, interconnected process where beginnings and endings merge into a continuous whole. As you let these ideas settle, there is something quietly moving in the notion of a universe without a true beginning. If the cosmos has undergone countless cycles before this one, then the moment you inhabit is just one crest in a vast, rhythmic unfolding. That thought can offer a sense of perspective. Your life, brief as it is, belongs to a continuum far older and far larger than anything the human mind can fully grasp. You are part of a story that stretches backward through epochs of unimaginable depth and forward into futures shaped by forces that transcend one lifetime. In that awareness, there is both humility and comfort, a reminder that you are carried by the same cosmic rhythms that have pulsed through eternity, and that within those rhythms, there is room to breathe, to reflect, and to rest. Chapter 6. Penrose's Cyclic Universe, CCC, when the remote future becomes the next Big Bang. Roger Penrose's conformal cyclic cosmology, often abbreviated as CCC, is one of the most imaginative and mathematically grounded attempts to describe a universe without a true beginning or end. Unlike the Big Bounce, which proposes a reversal from contraction to expansion, CCC envisions a sequence of cosmic epochs called aeons. Each aeon begins with what looks, from the inside, like a Big Bang and ends in a remote future in which the universe becomes increasingly sparse, cold, and dominated by radiation. The remarkable claim of CCC is that the end of one aeon can be smoothly connected to the beginning of the next. In this picture, the universe does not cycle through expansions and contractions, but through transformations of scale. The ultimate fate of one aeon becomes the starting point of the next, and the Big Bang is not an absolute origin, but a boundary between consecutive phases of cosmic evolution. CCC relies on a profound mathematical insight rooted in conformal geometry. Conformal transformations preserve angles and shapes while allowing distances and scales to change arbitrarily. Penrose's idea is that under certain extreme conditions, specifically when mass becomes negligible, the geometry of space-time can be stretched or compressed without altering its essential structure. In the far future of an expanding universe, when all massive particles have decayed or dispersed, and only massless radiation remains, the distinction between very large and very small scales becomes meaningless. Without mass, there is no preferred unit of length or time. In this setting, Penrose argues, the infinite future of one aeon can be rescaled to match the initial singularity of the next. This idea might seem abstract, but it is grounded in the expected behavior of the cosmos under continued expansion. As the universe evolves, stars burn out, galaxies drift apart, and black holes slowly evaporate through quantum processes. Over immense timescales, the universe becomes a vast, diffuse sea of photons and other massless particles. When only radiation remains, the universe can be represented in a conformally compactified form, meaning that its infinite future can be mapped to a finite boundary. Penrose proposes that this boundary is not a final endpoint, but the beginning of a new aeon, the Big Bang of the next universe. A key ingredient in this framework is the concept of gravitational entropy. Penrose has long emphasized that the low entropy of the early universe poses a serious puzzle for cosmology. The cosmic microwave background is remarkably uniform, and the early universe appears to have had extremely low gravitational clumping. This is important because matter arranged in a smooth, uniform distribution corresponds to low gravitational entropy, while matter organized into galaxies, stars, black holes, and other structures corresponds to high entropy. As the universe evolves, gravitational entropy increases, especially as black holes form. In Penrose's view, the uniformity of the early universe demands an explanation beyond simple initial conditions. CCC attempts to provide that explanation by asserting that the universe starts in a low entropy state because each aeon begins from the conformally smoothed out future of the previous one. In this picture, black holes play a special role. Over unimaginably long periods, black holes lose mass through a quantum process, sometimes called Hawking radiation. Eventually, every black hole evaporates, leaving behind only radiation. This helps eliminate all sources of mass, which is essential for the conformal rescaling that links one eon to the next. The evaporation of black holes thus becomes a cosmic reset, ensuring that the universe approaches a state in which scale loses its meaning. Penrose argues that the geometry of space in this regime becomes simple enough to match seamlessly onto the geometry near a Big Bang singularity. CCC is not merely a philosophical proposal. It makes testable predictions. One of its most intriguing claims is that signs of violent events near the end of the previous aeon could leave imprints in the cosmic microwave background of our current aeon. Specifically, the theory suggests that the final moments of supermassive black hole mergers could produce patterns that survive the conformal transition into the next eon. Penrose and collaborators have argued that circular features with unusually low temperature variation in the microwave background might correspond to such events. These features, often referred to as concentric circles, have been the subject of debate. Some analyses have claimed statistical significance, while others have argued that such patterns can arise from random fluctuations. The matter remains unsettled, but the fact that CCC makes concrete, falsifiable predictions distinguishes it from many other speculative cosmological ideas. Another aspect of CCC concerns the cosmological constant, the term associated with the accelerated expansion of the universe. In the remote future of a universe dominated by a cosmological constant, the expansion becomes exponential. Regions separate at such rates that interactions between distant parts of space cease. Penrose interprets this isolation as contributing to the washing out of structure, further promoting the massless, scale-free state necessary for the conformal transition. In this sense, the presence of dark energy is not an obstacle to CCC, but an essential ingredient. It drives the universe toward the simplified future boundary from which the next eon can begin. CCC also offers a radically different view of the arrow of time. In many cosmological frameworks, the increase of entropy defines the flow of time from past to future. In CCC, the arrow of time is tied to the transition between aeons, with each new aeon beginning in a low-entropy state inherited from the final conformal transformation of the previous one. Time, in this view, is not a universal parameter stretching infinitely backward or forward. Instead, each aeon has its own time direction, emerging from its specific initial conditions. The continuity between eons occurs not through conventional physical processes, but through geometric transformations that preserve the structure of space-time while altering its scale. One of the appealing features of CCC is that it does not require the universe to undergo contraction. Many cyclic models, including some versions of the Big Bounce, depend on a previous collapsing phase. CCC, by contrast, envisions all aeons as expanding universes. This avoids many difficulties associated with contracting cosmologies, such as the amplification of anisotropies or the buildup of entropy. Because the conformal transformation removes the notion of scale, the infinitely expanded future of an aeon can shrink to match the initial singularity of the next without requiring a reversal of expansion. There are, however, critiques of CCC. Some physicists question whether the conformal rescaling is physically justified, or whether the elimination of mass in the remote future is sufficiently complete to allow the transformation. Others point out that the evaporation of black holes and the decay of all massive particles depend on assumptions about particle physics and quantum gravity that have not been empirically verified. The debate is ongoing, and CCC remains a speculative but mathematically coherent contribution to the landscape of cosmological theories. Despite the uncertainties, CCC occupies an important place in contemporary discussions about the origin and fate of the universe. It addresses fundamental questions about entropy, the arrow of time, and the possibility of cosmological cycles. It provides a conceptual link between the physics of the very small, quantum processes governing fields and particles, and the physics of the very large, space-time geometry on cosmic scales. In doing so, it exemplifies the interplay between mathematics and physics that characterizes much of modern theoretical cosmology. CCC also offers a new kind of cosmic narrative. Instead of a universe that expands forever into emptiness or collapses into a singular endpoint, we encounter a cosmos that renews itself through an elegant geometric transformation. Each aeon contains its own galaxies, stars, and histories, yet each contributes to the next, passing on traces of its existence in faint patterns that might still be observable today. This continuity across aeons suggests that the universe is not a one-time occurrence, but part of a larger, ongoing process that transcends individual cosmic cycles. As you contemplate Penrose's vision, you may find a quiet resonance in the thought of a universe that flows from one aeon to the next, shedding its old structures and beginning anew. It is a model in which time stretches far beyond human experience, and yet in its vastness there is a sense of continuity and rhythm. Your life unfolds within a single moment of a single aeon, a fleeting interval in an unimaginably long cosmic sequence. And yet, that moment is part of a larger pattern, the universe renewing itself across ages, each beginning rising gently from the ashes of the one before. When you let your mind settle into this perspective, the concerns of the day soften, and you may feel a calm awareness that you are, in your own way, part of a timeless unfolding, carried by a cosmos that has cycled through eternity and will continue long after your thoughts fade into rest. Chapter 7. The Ekpyrotic and brane-collision universe, reality born from higher dimensions. Among the many attempts to describe the origin of the universe without invoking a singular explosion from an initial point of infinite density, the Ekpyrotic and brane-collision models stand out for their ambition and conceptual depth. They combine cosmology with ideas from higher dimensional physics, proposing that what we perceive as the Big Bang was not the creation of space-time from nothing, but the result of a dramatic event in a larger, multidimensional setting. In these theories, our universe is a three-dimensional surface, called a brane, embedded within a higher dimensional space. The beginning of our cosmic expansion, in this view, arose when our brane collided with another. The word Ekpyrotic comes from ancient Greek philosophy and means born from fire, evoking a cyclical cosmic conflagration. The modern scientific version of the idea emerged from work in high-energy theory and string-inspired physics. Paul Steinhardt and Neil Turok were among the first to articulate the Ekpyrotic scenario in a precise mathematical form. Their goal was to create a cosmological model that could reproduce the successes of the inflationary picture, such as the near uniformity of the cosmic microwave background and the formation of large-scale structure, without requiring a period of rapid inflation. Instead of smoothing the universe through exponential expansion, the Ekpyrotic model achieves the same effect through slow, ultra-contracting dynamics in which anisotropies and inhomogeneities are suppressed. In the brane-collision framework, which is closely linked to the Ekpyrotic scenario, the universe is not simply a three-dimensional space floating in emptiness. Instead, it is part of a higher dimensional structure that allows for parallel branes to exist side by side, separated by a small but finite distance in an extraspatial dimension. These branes are not rigid plates. They can move, oscillate, and interact. Gravity, and perhaps other types of fields, can propagate through the higher dimensional bulk, while ordinary matter is confined to the brane. In this setting, the Big Bang arises when our brane and a neighboring brane collide. The collision injects enormous energy into the brane, creating radiation and matter, and initiating a hot, expanding phase that resembles the early universe described by standard cosmology. This collision is not a singularity in the conventional sense. Instead of the infinite densities and curvatures predicted by classical general relativity, the brane-collision models provide a smooth geometric mechanism for the transition. The bounce occurs not through quantum gravitational repulsion, as in some big bounce scenarios, but through the dynamics of branes in the higher dimensional bulk. Because the branes themselves remain finite and well-defined, the geometry stays regular across the transition. One of the central achievements of the Ekpyrotic picture is its ability to produce nearly scale-invariant fluctuations in the density of matter, which serve as seeds for later structure formation. In inflationary models, these fluctuations originate from quantum perturbations stretched over enormous distances by rapid expansion. In the Ekpyrotic scenario, the fluctuations arise during a slow, contracting phase preceding the brane collision. As the scale factor contracts, certain modes of the perturbations become amplified in a way that mimics the inflationary predictions. The resulting spectrum of fluctuations can be very similar to that observed in the cosmic microwave background. However, reproducing the correct spectrum requires careful conditions. The contraction must occur in a regime dominated by fields with specific properties, often involving scalar fields with steep negative potentials. These fields drive a contraction that homogenizes the universe, smoothing out irregularities instead of amplifying them. Because of the slow and controlled nature of this contraction, anisotropies that might otherwise grow are suppressed, resulting in a universe that, after the bounce, appears extremely uniform on large scales. Another appealing feature of the Ekpyrotic and Cyclic models is their approach to entropy and cosmic evolution. Unlike the traditional big bounce models that depend on actual contraction of the physical universe, the Ekpyrotic picture can be embedded into a cyclic scenario where each cycle consists of a period of expansion followed by a long period of slow contraction, and then a collision that initiates the next expansion. Entropy generated in each cycle can be diluted over the vast duration of expansion and contraction, avoiding the accumulation of disorder that plagues simpler cyclic models. In this more refined interpretation, each new cycle begins with conditions similar to those of the preceding one, allowing the universe to repeat its large-scale evolution over immense timescales. The brane collision model also offers distinctive predictions. For instance, it predicts that the gravitational wave background produced in the early universe should be extremely weak, much weaker than the levels predicted by most inflationary models. This difference provides a possible observational test. If future measurements of the polarization of the cosmic microwave background fail to find the gravitational wave signatures expected from inflation, the Ekpyrotic scenario might become more attractive. Conversely, a strong detection could rule it out or force significant modifications. Despite its conceptual richness, the Ekpyrotic framework faces challenges. One difficulty lies in ensuring that the transition from contraction to expansion is stable and free of pathological behaviors. The physics of brane interaction is complex, and while simplified models capture the essential features, a complete understanding of the brane collision requires deeper insight into high-energy physics and quantum gravity. Another challenge involves matching the predictions for cosmological observables with increasing precision. While the Ekpyrotic models can reproduce the overall pattern of density fluctuations, certain detailed features, such as non-Gaussianity, remain areas of active research. Nevertheless, the Ekpyrotic and brane collision scenarios remain serious contenders in theoretical cosmology. They offer a coherent alternative to the idea that inflation is required to explain the early universe. By invoking higher dimensional physics, they broaden the conceptual landscape and suggest ways in which cosmic origins may be tied to structures beyond our observable universe. The notion that our cosmos was born from the collision of higher dimensional branes elevates the story of origins into a richer geometric framework, merging cosmology with the deeper theoretical structures that emerge from attempts to unify gravity with quantum mechanics. These models also raise intriguing philosophical questions. If our universe is one brane among many, then its birth becomes part of a larger, multidimensional dance. The event we call the Big Bang may have been the meeting of two immense surfaces drifting through a higher dimensional ocean. Perhaps other branes exist elsewhere in the bulk, undergoing their own cycles of approach and separation. The universe we see is then only a slice of a grander reality, hidden from us, except at the moment of cosmic collision. As with all speculative cosmological theories, the Ekpyrotic picture remains incomplete. It depends on assumptions about extra dimensions that are not yet confirmed and on mathematical structures still under development. But it highlights an important point. When current theories reach their limits, exploring imaginative extensions of established frameworks can reveal new possibilities. The Ekpyrotic universe illustrates how a profound shift in perspective, viewing our cosmos not as isolated, but as part of a larger multidimensional structure, can reshape the way we understand time, origins, and the evolution of space. If these ideas are correct, then the universe you inhabit is part of a cycle that stretches far beyond ordinary human timescales. Its birth was not a singular event, but the latest moment in an ongoing sequence of cosmic transformations. Perhaps countless cycles preceded this one, each with its own galaxies, structures, and histories, now erased except for subtle imprints in the physics of the present. As you reflect on this vision, imagine the cosmos as a vast multidimensional landscape in which branes glide and evolve, occasionally meeting in events that give rise to entire universes. You live within one such universe, a fleeting moment in a process that spans infinities. And yet the very fact that you can contemplate this process is something extraordinary. When you let your thoughts drift across these higher dimensional possibilities, a calm perspective settles in. Even if the cosmos is born of collisions beyond your perception, your presence within it is real and meaningful, anchored to the quiet flow of time in your own corner of the brain. Chapter 8. Hawking and Hartle's No-Boundary Universe, a cosmos with no beginning. Among the many attempts to describe the earliest moments of the universe, few are as bold or mathematically striking as the no-boundary proposal developed by Stephen Hawking and James Hartle. This model attempts to answer one of the most profound questions in cosmology. If the universe began with the Big Bang, what happened before? Traditional formulations of the Big Bang contain a singularity where density, temperature, and curvature diverge. This singularity is not a physical object, but a sign that classical general relativity cannot describe the earliest instant of cosmic history. Hawking and Hartle sought a way to remove the singularity, not by avoiding the Big Bang, but by reinterpreting what the beginning of the universe actually means. Their solution was to apply quantum mechanics to the geometry of space-time itself, proposing that time, at the earliest stages of the universe, behaved in a fundamentally different way. The no-boundary proposal introduces the idea that time may not have always existed in the familiar form we experience. Hawking and Hartle suggested that close to the supposed beginning of the universe, time can be treated like a spatial dimension, a direction not associated with causal flow, but with geometric structure. In this regime, the distinction between time and space dissolves, and the universe can be represented using a mathematical transformation called imaginary time. Imaginary time is not imaginary in the colloquial sense, but a technical tool in quantum field theory that enables the smoothing of space-time geometries. When time behaves like a spatial dimension, The singularity that appears in classical models can be replaced by a smooth, rounded geometry. This rounded geometry is often compared to the surface of a sphere. On a sphere, no point can be identified as a boundary or an edge. One location may serve as a pole, but it is not a beginning in the temporal sense. In the no-boundary model, the early universe is described using a similar structure. There is a region where the geometry transitions from the realm of imaginary time to ordinary time. But this transition does not require a singular boundary. The universe simply emerges from a smooth, finite geometry. The Big Bang, in this view, is not a moment of creation from nothing, but the point where time begins to behave in the familiar way, flowing forward according to classical physics. This conceptual shift requires a quantum mechanical description of space-time. Hawking and Hartle developed a framework known as the wave function of the universe, which assigns probabilities to different possible geometries and field configurations. Instead of asking what the universe was at the first instant, the no-boundary proposal asks what configurations of space-time are most probable given the rules of quantum mechanics. The proposal states that the most natural and mathematically consistent histories are those with no boundary at the beginning, analogous to a sphere with no edge. The universe therefore arises in a smooth, finite state, consistent with quantum principles and without the singularities that plague classical descriptions. One of the appealing features of the no-boundary model is that it provides a natural explanation for the early homogeneity and isotropy of the universe. In classical cosmology, the near-uniform temperature of the cosmic microwave background requires mechanisms such as inflation to smooth out irregularities. While the no-boundary proposal does not eliminate the need for inflation, it predicts that smooth and nearly uniform universes have higher quantum probability than jagged, irregular ones. The geometry near the transition from imaginary to ordinary time tends to favor configurations that evolve into the smooth, expansive cosmos we observe today. This preference arises from the mathematical form of the wave function and is consistent with both inflationary and non-inflationary cosmologies. Another important implication of the no-boundary proposal concerns the arrow of time. In classical cosmology, time's direction is associated with rising entropy. The no-boundary model reframes this idea by suggesting that the low entropy state of the early universe arises naturally from the smoothness of the no-boundary geometry. Instead of requiring special initial conditions or fine-tuning, the model implies that low entropy is a natural consequence of the highest probability configurations in the quantum ensemble. As the universe expands, entropy grows, and the familiar arrow of time emerges. Although the no-boundary universe is a powerful theoretical framework, it remains challenging to test observationally. The proposal makes probabilistic predictions about the likelihood of various cosmological parameters, such as the density fluctuations that give rise to galaxies and clusters. By comparing these predictions with high-precision measurements of the cosmic microwave background, physicists can place constraints on the model. Some analyses suggest that certain versions of the no-boundary proposal are compatible with observational data, while others find discrepancies. These debates reflect the difficulty of translating quantum mechanical descriptions of the universe into concrete predictions. One area of active research involves the relationship between the no-boundary model and inflation. early formulations of the proposal implied that universes with small amounts of inflation were more probable than those with large amounts. However, observational data strongly favors significant inflation to explain the structure of the cosmic microwave background. This tension has led to refinements and extensions of the no-boundary wave function, attempting to reconcile the theory with empirical evidence. Some modified versions of the proposal suggest mechanisms through which inflation can be highly probable while preserving the mathematical elegance of the original formulation. The no-boundary proposal also intersects with ongoing work in quantum gravity. The mathematical tools that describe the earliest geometry of the universe rely on approximations that may eventually be replaced by more complete descriptions arising from candidate theories such as loop quantum gravity or string theory. In this sense, the no-boundary idea might represent a provisional picture, a stepping stone toward a deeper understanding of how space-time behaves under extreme conditions. Yet, even if the no-boundary model is superseded, its conceptual contribution remains significant. It demonstrates that the beginning of the universe does not necessarily require a singularity or a literal moment of creation. Instead, the beginning can be understood as a smooth geometric transition, grounded in quantum principles and consistent with the known laws of physics. Another philosophical implication of the no-boundary universe concerns the question of before. In classical thinking, it is natural to ask what came before the Big Bang. The no-boundary model reframes the question by asserting that before loses meaning near the earliest stages of the universe. Time itself is a property of the universe, not a backdrop against which the universe unfolds. When time behaves like a spatial dimension near the no-boundary region, it ceases to support questions about causality or sequence. The universe simply is, emerging from a quantum geometry that has no boundary in time. This perspective challenges intuitive notions about origins. Instead of seeking a cause that preceded the universe, the no-boundary model suggests that the universe is self-contained. Its earliest state is defined by the geometry of the wave function, not by an external trigger. This idea has echoes in both philosophy and mathematics, where the most elegant solutions often arise from boundary conditions rather than external forces. For Hawking, this elegance was one of the strongest arguments in favor of the no-boundary universe. He famously remarked that asking what happened before the no-boundary state would be like asking what lies south of the South Pole. The question assumes a direction that does not exist. As the no-boundary model continues to be explored, it remains one of the most influential attempts to blend quantum mechanics with cosmology. It provides a compelling alternative to singularity-based origins while preserving the predictive power of the Big Bang framework. It also reminds us that the universe may be far stranger than classical intuition allows. The fabric of space-time itself may undergo transformations at the earliest moments that defy ordinary temporal understanding, revealing a cosmos that is self-organizing, smooth at its origin, and inherently quantum in nature. Reflecting on this idea, you may find a quiet sense of wonder. The notion that the universe emerged smoothly from a realm where time itself loses its meaning invites a gentler view of existence. If the cosmos has no true boundary, no hard edge where everything begins, then perhaps our own lives too are part of a larger, continuous flow. You are carried along on a wave of cosmic history that stretches back through quantum geometry and forward into the unknown. And in this vast, boundaryless expanse, there is space to breathe, to soften the weight of the day, and to rest in the knowledge that beginnings are never as sharp as they seem. Chapter 9. The Universe from Nothing, Quantum Tunneling, Vacuum Fluctuations, and Zero Total Energy. Among the most intriguing and controversial ideas in modern cosmology is the claim that the universe may have arisen from nothing. This phrase can be misleading because in physics, nothing rarely means the complete absence of all structure or law. Instead, it refers to a state without classical matter, without space as we understand it, and without time flowing in the familiar sense. In this context, nothing is a quantum vacuum, a state governed by the rules of quantum mechanics, where fluctuations, virtual particles, and probabilistic transitions still occur. The notion that the universe could emerge from such a state rests on two key ideas: quantum tunneling and the possibility that the total energy of the universe may sum to zero. Together, these concepts form a coherent framework for understanding how cosmic expansion could begin without requiring an external cause or a pre-existing world. Quantum tunneling is one of the most counterintuitive aspects of quantum mechanics. In classical physics, a particle trapped in a potential well cannot escape unless it has sufficient energy to overcome the barrier. Quantum mechanics, however, introduces probability into the foundations of motion. A particle has a non-zero probability of appearing on the other side of a barrier, even if it does not possess the energy needed to cross it classically. This process is known as tunneling, and it is essential to many physical phenomena, from radioactive decay to the operation of modern electronics. If quantum tunneling can allow particles to move through classically forbidden regions, it is natural to ask whether entire universes could undergo similar transitions. This question led physicists to explore models in which the universe as a whole tunnels from a quantum vacuum state into an expanding space-time. This transition is sometimes described as the universe nucleating from nothing. The concept derives from models of bubble nucleation in quantum field theory. In such scenarios, the vacuum can exist in multiple states, including a metastable one that is not at the lowest possible energy. Quantum fluctuations can cause a bubble of true vacuum, representing a lower energy configuration, to form. Once formed, this bubble expands, releasing energy and restructuring the surrounding space. When applied to cosmology, the idea suggests that a small bubble of spacetime containing an inflaton field could tunnel into existence from a quantum vacuum. This bubble would then undergo rapid inflation, smoothing and expanding into a universe like our own. Such a process raises a profound question. How can something arise from nothing without violating conservation of energy? Here, the second key idea enters the picture. The total energy of the universe may be exactly zero. This may seem surprising, but it follows from general relativity and our understanding of gravitational energy. In physics, energy can be positive or negative depending on its source. Ordinary matter and radiation contribute positive energy. Gravitational fields, however, contribute negative energy. When a mass is assembled from dispersed particles, gravitational potential energy decreases, becoming more negative. In cosmology, the positive energy of matter and the negative energy of gravity may balance perfectly. If the total energy is zero, then the creation of the universe would not violate conservation laws. The cosmos could arise as a quantum fluctuation, much like the temporary appearance of virtual particles in the quantum vacuum. While virtual particles normally annihilate quickly, the universe could persist because the balance of energies allows it to evolve into a stable configuration rather than collapsing immediately. This idea has deep roots in theoretical physics. It aligns with the observation that the large-scale geometry of the universe is close to spatially flat, suggesting that matter and gravitational energy offset each other. In such a flat or nearly flat universe, the balance required for zero total energy becomes plausible. Moreover, inflation provides a mechanism for allowing a small quantum fluctuation to grow into a universe of immense size. The inflaton field, with its repulsive gravitational effect, can drive rapid expansion while maintaining the overall energy balance. The concept of the universe arising from a quantum vacuum does not imply that the universe emerged randomly or without rules. Quantum mechanics, general relativity, and field theory impose strict constraints on how such a transition can occur. The nothing from which the universe could arise is not an empty void, but a state described by mathematical laws. In this sense, the question of why there is something rather than nothing becomes a question about why the laws of physics have the form they do. Some philosophers and physicists argue that the quantum vacuum is not truly nothing because it possesses structure and possibilities. Others note that true nothingness may be a concept outside the scope of physics, which deals only with describable states of reality. The idea of cosmic tunneling raises questions about the nature of time. If the universe emerged from a quantum vacuum, what does before mean? In many formulations, time itself is a derived concept that arises only after the tunneling event. The quantum vacuum state does not contain time as we understand it. Instead, time emerges once the expanding spacetime begins to form. This is similar to the no-boundary proposal described earlier, in which time becomes meaningful only within the universe, not as something extending outside or before it. In the context of tunneling models, the question what happened before the universe existed becomes meaningless because the framework does not include a temporal direction prior to the tunneling event. Quantum cosmology offers multiple ways to describe the tunneling process. Some models treat the universe as a closed system described by a wave function that encodes all possible configurations of space-time and fields. In this view, the tunneling event corresponds to a transition from a state of minimal geometry to one in which space-time begins to expand. Other approaches use analogies to barrier penetration in quantum field theory, treating the early universe as a bubble forming within a larger quantum state. Despite these differences, the core idea remains the same. A transition occurs from a non-classical state to a classical expanding universe, driven by the probabilistic rules of quantum mechanics. While these concepts are compelling, they remain speculative and difficult to test directly. The tunneling process, if it occurred, would have taken place at scales far beyond the reach of current experiments. However, quantum tunneling cosmologies make predictions about the initial conditions of the universe, such as the expected behavior of the inflaton field or the likely geometry of early spacetime. By comparing these predictions with observations of the cosmic microwave background, physicists can place constraints on which tunneling models are viable. Some versions predict specific patterns of fluctuations or correlations that might eventually be detectable. The question of whether the universe could arise from nothing touches on deep philosophical issues. If the universe began as a quantum fluctuation, One might ask why the laws of quantum mechanics exist at all. Does this framework imply that existence is inevitable given certain mathematical structures, or does it suggest that physical laws themselves are contingent? These questions move beyond the scope of empirical science, yet they are inspired by scientific insights. They illustrate how cosmology can guide philosophical reflection without claiming to provide definitive metaphysical answers. From a scientific standpoint, the universe from nothing models offer a natural explanation for why the cosmic expansion began without invoking external agents or pre-existing materials. They provide a framework consistent with conservation laws, general relativity, and quantum mechanics. Although they do not describe absolute nothingness, they describe the closest thing physics can meaningfully analyze: a state without space-time, containing only the potential for space-time to emerge. As you reflect on this idea, consider the quiet beauty embedded within it. The thought that the vast universe could arise from a delicate quantum fluctuation reveals an elegance in the underlying fabric of reality. What seems immense and ancient may trace its origin to a moment outside the familiar flow of time. And just as the universe emerged from a state where nothing resembled our world, your own existence unfolds from moments of uncertainty and change. In the vast silence of the cosmos, born from a balance of energies so subtle it sums to zero, you find yourself here, breathing, thinking, reflecting. Perhaps there is comfort in knowing that even from near nothingness, something extraordinary can arise. Chapter 10. How we search for clues, what modern science can actually test. Cosmology deals with the largest scales of space and time, exploring questions that stretch far beyond the limits of ordinary experience. Theories about the origin of the universe, whether involving inflation, bounces, higher dimensions, or quantum tunneling, push the boundaries of what can be observed, measured, or even conceptualized. Yet, despite the abstract and sometimes philosophical nature of these questions, modern science has developed sophisticated methods for testing cosmological ideas. Our ability to gather evidence hinges on the fact that even the most exotic early universe models must ultimately produce a universe that evolves into the one we see today. The cosmos carries a memory of its past in its large-scale structure, radiation fields, elemental composition, and gravitational patterns. By studying these remnants with increasing precision, scientists can evaluate which origin theories are viable and which must be revised or discarded. One of the primary tools for testing cosmological theories is the cosmic microwave background, a faint glow of radiation that fills the universe. This radiation was emitted when the cosmos was still young, only a short time after the beginning of the hot dense phase traditionally associated with the Big Bang. Because the cosmic microwave background has traveled across the universe largely undisturbed, it preserves a snapshot of early conditions. This snapshot contains subtle temperature variations that encode information about quantum fluctuations, matter distribution, and the geometry of space. Different theories of the universe's origin predict different statistical patterns in these temperature variations. For example, inflationary models often predict a nearly scale-invariant spectrum of fluctuations, meaning that structures on different size scales should exhibit similar patterns. Some inflationary models also predict a specific type of polarization signal generated by gravitational waves from the early universe. The detection or absence of such signals provides important clues. If gravitational wave imprints were found with amplitudes matching certain inflationary predictions, it would support those models. If such signals remain absent even with extremely sensitive measurements, it could favor alternative theories such as the Ekpyrotic model, which predicts a much weaker gravitational wave background. Beyond the microwave background, large-scale structure surveys also play a crucial role. Galaxies and clusters of galaxies did not form randomly. Their distribution reflects the earliest perturbations in matter density. Surveys that map millions of galaxies allow scientists to reconstruct the statistical properties of matter on cosmic scales. These data can test whether the predicted patterns of early fluctuations match what is observed today. The way galaxies cluster, the formation of cosmic voids, and the growth of structure over time all provide windows into the physics of the early universe. The dynamics of cosmic expansion also offer essential clues. Observations of distant supernovae, combined with precise measurements of galaxy distributions and the cosmic microwave background, reveal how the expansion rate of the universe has changed over time. These measurements constrain the energy content of the universe, including dark energy and dark matter. Many origin theories, especially those involving modifications of gravity or exotic scalar fields, predict subtle differences in the expansion history. By comparing the observed expansion pattern with theoretical predictions, scientists can narrow the range of viable models. Another promising avenue involves primordial abundances of light elements. The early universe underwent a period during which hydrogen, helium, and small amounts of other elements were synthesized. This process, called primordial nucleosynthesis, depends sensitively on the density of baryonic matter and the expansion rate at that time. Different origin scenarios may alter these conditions in subtle ways. By comparing observed abundances with theoretical expectations, scientists can test whether the early universe behaved according to standard assumptions or whether new physics is required. Even gravitational waves themselves provide new opportunities. The universe is filled with gravitational wave backgrounds produced by a wide variety of processes, mergers of compact objects, phase transitions in the early universe, and the stretching of space-time during inflation. As detectors become more sensitive and new observational methods are developed, scientists may eventually detect primordial gravitational waves that trace back to the earliest moments of cosmic history. These signals could directly test whether inflation occurred, whether brane-collisions took place, or whether other exotic phenomena contributed to the universe's initial conditions. Beyond these observational methods, particle physics experiments also contribute to cosmology. High-energy collisions in accelerators recreate conditions that existed when the universe was extremely hot and dense. By probing the behavior of quantum fields, symmetry breaking, and exotic particles, scientists can infer whether certain early universe models are physically plausible. For example, inflationary models often depend on the existence of hypothetical scalar fields. Discovering or ruling out such fields experimentally would refine our understanding of inflation's feasibility. Similarly, searches for dark matter particles clarify whether theories involving modifications of gravity or higher dimensional physics are consistent with the actual contents of the universe. Neutrino astronomy provides another emerging avenue. Neutrinos interact only weakly with matter, allowing them to travel across cosmic distances almost unimpeded. background of relic neutrinos from the early universe is predicted to exist, analogous to the cosmic microwave background, but formed much earlier. Although detecting this neutrino background is extraordinarily difficult, progress in ultrasensitive detectors brings the possibility closer. The properties of these relic neutrinos would reveal details about processes occurring when the universe was far younger than any epoch observable through light. Modern cosmology also uses simulations, vast computational models that evolve billions of particles or fields under the laws of physics. These simulations allow scientists to test whether a given theory produces structures that match observed galaxies, clusters, and cosmic filaments. Differences between simulated universes and observed ones can indicate where theoretical models need refinement. While simulations cannot directly confirm early universe physics, they provide a bridge between theoretical predictions and measurable phenomena. Despite these promising strategies, many cosmological theories operate near or beyond the limits of direct testability. Concepts like higher dimensional branes, conformal geometries in imaginary time, or quantum tunneling from a vacuum state are difficult to probe experimentally. However, modern theoretical physics demands internal consistency. A successful cosmological theory must be mathematically coherent, must align with known laws of physics, and must not contradict any observational evidence. Even without direct tests, theories can be constrained by their compatibility with existing data. Moreover, scientific progress often emerges from the convergence of different lines of evidence, rather than a single definitive measurement. If a theory consistently predicts features that align with observed structure, cosmic microwave background patterns, gravitational behavior, and other phenomena, it gains credibility. Conversely, if a theory requires fine-tuned assumptions or contradicts well-established measurements, it loses viability. In this way, cosmologists gradually refine our understanding of the universe's origin, even if certain aspects remain beyond reach. The search for cosmic clues also highlights the interplay between theoretical creativity and empirical discipline. Some of the most imaginative ideas in cosmology, such as the no-boundary universe or the Ekpyrotic scenario, began as attempts to solve conceptual problems. Over time, they evolved into frameworks that made concrete predictions. Even when those predictions are difficult to test, they encourage new observational strategies and new technological innovations. As measurement techniques improve, the boundary between the testable and the speculative shifts. Instruments that map cosmic radiation more precisely, telescopes that observe the universe at incredible distances, and detectors capable of capturing minute gravitational fluctuations all expand our scientific reach. What was once untestable becomes testable, and ideas that seemed purely theoretical gain empirical footing. In this sense, the history of cosmology is a story of slowly illuminating a darkness that once appeared impenetrable. There's also a subtle philosophical dimension to these efforts. When scientists test theories about the origin of the universe, they are indirectly testing ideas about the nature of existence itself. Is the universe a single, self-contained entity with a unique beginning? Or is it part of a larger landscape of possible realities? Are the laws of physics fixed and immutable, or do they vary across different cosmic regions? These questions touch on meaning, identity, and the limits of human understanding. While science cannot answer philosophical questions directly, it shapes the context in which those questions are asked. Testing cosmological theories requires a willingness to accept uncertainty. The early universe pushes scientific concepts to their limits, where quantum mechanics and general relativity intersect in ways not yet fully understood. Yet this uncertainty does not diminish the pursuit. Instead, it underscores the remarkable fact that the universe leaves traces of its earliest moments, encoded in everything from the distribution of galaxies to the faint polarization of ancient radiation. The cosmos tells its story quietly, but with precision for those who know how to listen. As you reflect on how we search for clues about the universe's beginning, you may feel a sense of humility and wonder. Modern science reveals a cosmos where countless small imprints, tiny temperature fluctuations, faint gravitational echoes, subtle patterns in the sky, hold the key to understanding vast and ancient processes. It reminds you that even the most overwhelming mysteries can be approached by patient observation and careful reasoning. And perhaps, as the night settles around you, this realization brings a gentle calm. You are part of a universe that is knowable, at least in fragments, even as it surpasses comprehension. In the quiet of this moment, you can rest knowing that the cosmos is still telling its story, and we are still learning how to read it. My friend, if you're still awake, thank you for exploring the universe with me tonight. There are so many more mysteries waiting for you, gently told, just like this one. So if your eyes are open, feel free to choose another video and keep drifting through the cosmos. And if sleep is already pulling you in, I wish you the sweetest dreams among the stars. Good night.